can highlight that a period that repeats itself over regular intervals is called a periodic function. And we call the length of each of these intervals the period. So those are two new definitions, a periodic function and a period. And they have the graph of y equals sine x given to you here. Okay, right beside it, I'm not happy with the scale that they've given, and you need to be able to graph the sine graph really quickly. So the way that we're going to graph the sine graph really quickly, and what I'm going to get you to draw right beside this, is you're going to use your axes family. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. And if you use your axes family, you will get all of the maximums and minimums and the points that are in the middle and be able to graph the curve quickly and easily. So sine is your y coordinates. You know that sine of 0 is 0. Sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2 is negative 1. And sine of 2 pi is back to 0. And just like the parent graphs that you had in our first unit, you will need to be able to think of this graph quickly and be able to label those 5 points. Now while you're drawing that down, a couple of things to notice on here. Do you notice that the period of your sine graph, how long does it take to repeat itself, is 2 pi, exactly 1 time around your circle. Once you go around your circle, then everything repeats itself for sine. We can measure that when you're trying to figure out the period. You can take any point on your graph. So if I take this point going up, I have to say, when is the next time my graph is at that point going up again? Well, here it's at that point but going down. It doesn't get back to going up again until 2 pi. So the distance between 0 and 2 pi is our period. Sometimes students use a maximum to another maximum as a way to calculate how much is the period in. Sometimes students use a maximum to a minimum and double it. Does it make sense that if it travels from here to here and it takes pi, it's going to take pi to get back to the maximum again, and your period would be 2 pi. No matter which point you choose to measure how long it takes to repeat itself, that value is going to be the same. For your sine graph, your period is always going to be 2 pi. Some other definitions, if we're highlighting more stuff here, so we've got our period being 2 pi. You can highlight that. The distance from the center line to a maximum or center line to a minimum is something called an amplitude. And the amplitude of this graph is 1. The domain is everything. The zeros, okay? The zeros are, if we started listing them, maybe we'll do this off to the side just to think about it a little bit. The zeros are where you have x-intercepts. You have one at 0, you have one at pi, at 2 pi, 3 pi, 4 pi, also in the negative direction, negative pi, negative 2 pi, dot, 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 dot. You might notice a pattern. It is an integer multiplied by pi. So when we want to write them all down, this is how you would write it. K times pi, where k is an integer. That would include 0. It would include 1 pi, 2 pi, 3 pi, all the positive ones, and also all the negative ones. For a sine graph, we have a maximum of 1, a minimum of -1, so our range is between -1 and 1. This is our sine graph. Again, you're going to be able to draw it quickly just using your axes family. I'm not actually happy with the scale that the textbook gave. It's not important to have pi over 3 on there and 2 pi over 3. You just need to have your axes family. Next, we have our cosine graph. Our cosine graph also has a period of 2 pi. Amplitude is still 1. Period is 2 pi. And right beside this one, just like we did for sine, use your axes family to draw your cosine graph. Again, remember on your unit circle, cos is your x-coordinate. So at 0, your x-coordinate is 1. At pi over 2, it's 0. At pi, your x-coordinate is -1. 3 pi over 2, it's 0. And at 2 pi, it's back to 1 again. So for cos, at 0, it's at a maximum. How long does it take to get to another maximum? That distance is 2 pi. That is your period. So just like sine, the domain is everything. But now the zeros, and we're going to think about this a little bit, off to the side. If we start listing them, we would have 1, 0 at pi over 2, then 3 pi over 2, then 5 pi over 2, then 7 pi over 2, dot, 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 and same thing in the negative direction. So mathematically, how do we write all of these zeros? Okay? And there's 2 ways that we can go about this. I'll show you 2 methods. You can decide which one you like better. First of all, the one that students notice the most is that you always have a pi over 2, but you have an odd number there. 3, 5, 7, 9, either positive or negative. So we need to know, how do you make an odd number? Mathematically, if you take any integer, any positive or negative whole number, and double it, this makes it even. Does that make sense? If you take 5, double it, you get 10. Take 7, double it, you get 14. Take 3, double it, you get 6. Take 6, double it, you get 12. Whenever you double something, you will always get an even number. So in order to get an odd number, you would just need to add 1 to an even number and multiply it by pi over 2 and explain that k is any integer. So this is method number 1. Method number 2 looks at saying, let's start with one of our zeros at pi over 2. How much of a jump is it to the next one, right? Here I've got my x-coordinate equal to 0. Down here's my next one. Can you see that that distance on your unit circle is jumping plus pi forwards, 180 degrees. And then 180 degrees again, you'll be back at the top. So another way that you could write all of the zeros is you could start with one of them. So let's start with pi over 2. And then add or subtract pi as many times as you like. So if we're at pi over 2, and we add pi, as many times as you want, you will always end at either the top or the bottom of your unit circle. So we could also write the zeros as pi over 2 plus k pi. So when you're asked for the zeros of cosine and asked to write the general form of them, you can choose whichever one of those two makes the most sense to you. Either starting with 1 and figuring out what the distance between the hops are, or noticing the pattern that they're all odd number times pi over 2. So how do we write an odd number? 2k plus 1. This. That 2k plus 1 makes any odd number. And just like sine, we've got a maximum of 1, a minimum of -1, so the range is also from -1 to 1. Now I know I've highlighted the word amplitude in each of those questions. We can highlight the official definition of amplitude. Amplitude is the distance from the center line to either the maximum or the minimum. And since it's the distance, your amplitude will always be positive. Before we do example 1, we're also going to do the graph at the bottom of page 516, the graph of tan of x. So again, we're going to use our axes family for tan of x. I'll get you to draw this beside it. On your unit circle on your axes family, when tan is undefined, you are going to draw a vertical asymptote. So at pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2, those will all be asymptotes for tan. The other part of your axes family, at pi, 0, and 2 pi, tan is always 0.
You don't know who that's from yours, do you?
Yes, Word. And I got more tracing paper. Can you trace it? Okay, you want to look? Okay. So to figure out the period of tan, you could either look, okay, at 0, it's in the middle going up. When does that happen again? At pi. So the period is not 2 pi for tan. The period of tan is pi. Or you can measure between one asymptote and the other asymptote and figure out that that distance is pi as well. And you might notice that the graph of tan looks very similar to an x-cubed graph. Okay, but it's a whole bunch of little x-cubed graphs with asymptotes repeated. Whereas the x-cubed graph just keeps getting wider and wider and wider, the tan graph has a bunch of asymptotes. So our characteristics, was that too quick? All right, I'll go back. I'll go back, no problem. again, on the tan graph off to the side, you can highlight the period as pi. There is no amplitude off to the side. If we wanted to write an equation of every single asymptote, notice that the asymptotes are at the same place where cos is 0. So the equations of the asymptotes are at the same place where cosine is 0, and that may make sense because remember the big idea that tan of theta is sine of theta over cos of theta, and wherever cos of theta is 0, you would be dividing by 0. So if you're dividing by 0, that's not allowed. Those are all the places where tan is undefined. So your asymptotes equation, every single one of them, can be written as 2k plus 1 pi over 2. Same thing, where is tan equal to 0 is exactly the same as where cos is 0. So your zeros are all going to be k pi, just like the zeros of sine. The domain, the way that we write the domain is, and actually this one, we'll write it here. This is a better form than the textbook. You write x can't equal, and then you write the zeros of cosines. So when we're writing equations of asymptotes, asymptotes are equations that always have an equal sign. When you transfer that to your domain, you write a line through the equal sign, because in your domain, those are the places where it is not allowed. And since the graph goes up and down forever, the graph of tangent, the range of tangent is everything. So now we're going to take these three graphs. As soon as you can, you're going to have them memorized so that you can graph them quickly and easily. So again, you're going to have to really know your axes family well from your unit circle, because that's what you use to graph these. And then we're going to do each of these questions. We'll start with example 1. And the questions are just going to ask us to determine the amplitude. We are also going to graph each of them. And what we're going to notice is that for sine and cosine, there is going to be a shortcut that we can use for graphing. So first of all, in A, using transformations. If we were using transformations, there is a 2/3 that is added in front of the function. Can you see that that 2/3 is outside of the function? This will be a vertical compression. You are going to multiply all your y values by 2/3. So in your head, you would have your original sine graph. So what I would do to draw your sine graph, what you're going to do is you're going to label your period of 2 pi and divide it into 4 equal sections, which is just your axes family. And we know it has a maximum of 1 and a minimum of -1. This is your sine graph. If you multiply all 5 of those points, multiply your y coordinate by 2/3, the following is going to happen. First of all, we'll still have 2 pi divided by, and our whole axis family listed here, because those are our x values, and our x values are not going to change. And can you see that each of the x-intercepts, where y is equal to 0, if you multiplied y by 2/3, and the y-coordinate is 0, they're not going to change. But this point right here, right, this point where it's pi over 2, comma 1, if I multiply my y-coordinate by 2/3, can you see that now you would have pi over 2, comma 2/3. So what I'm going to do is I'm going to write my maximum value is now going to be at 2/3. And in the same sense, my minimum value is now going to be at -2/3. So here's the graph of my new equation. And the question asks, what's the amplitude? The amplitude is the distance from the center line to a maximum. The amplitude is 2/3. In part B, again, we notice that we have got a -4 in front of our coast graph. This is going to be a vertical reflection and a vertical stretch. You would multiply your y values by -4. So as far as looking at the graph of this one, well, a normal cosine graph, you would label your axes family, pi, pi over 2, and 3 pi over 2, maximum of 1, minimum of -1. A normal cosine graph starts at a maximum, then goes center line, minimum, back to maximum. There is our normal cosine graph. And what we're going to do is we are going to multiply all of our y-coordinates by -4. So if I think about my graph now, again, since my x-coordinates aren't changing, I'm going to just write down my axes family again. Can you see that at your x-intercepts, those ones are not going to change because you're multiplying your y values by -4. But we had the point 0, 1. Can you see that now, if you multiplied your y by -4, you would now have 0, -4. This will be your new minimum. And your new maximum, right, because we had this point at pi -1, if I multiply my y-coordinate by -4, I'm now going to have a new maximum at +4. Same thing at 2 pi, it will be back down to -4. So our graph will look like this. And our amplitude, the distance from the center line to the maximum, is +4. And these two examples, if we did another 2 or 3, you'd really start to see this pattern. Maybe you see it already. Does it make sense that whatever your vertical stretch or compression is, that's going to be your amplitude? If your amplitude was 1, and you stretch it by 3, it's now going to be 3. When we stretched it by a -4, your amplitude was 1, now it's +4. Amplitude is always positive, so even though there was a reflection in part B, we would still say our amplitude is positive 4. And this is going to give us a shortcut for graphing. Did you notice that I didn't take the 5 points and do the arrow diagram like we normally did with transformations? That's because it's a little bit annoying because you have to write pi every single time, and we are going to develop a shortcut for these. The shortcut that you're going to notice with your amplitude or with a vertical stretch or compression is that your vertical stretches and compressions are going to affect your maximum and your minimum. On a normal sine graph, they're 1 to -1. When we multiplied by 2/3, now they're -2/3 to 2/3. In the second one, a cosgraph, normal max and min are 1 and -1. When we multiply by 4 or -4, they're now 4 and -4. We're always going to use our axes family, our period divided into 4 equal sections, to be able to graph this. Okay, I'd like you to circle questions 3A and B, 4, 5, and 9.